Hello everyone, welcome to the new class of solid state physics. And today we are going to discuss more about Drude's law, and we are going to dedicate this class to the failures of Drude's law and how the need of a new scientific theory, which was basically the Sommerfeld model, which is the quantum model, arises out of the necessity that the Drude's model is not giving us the right answer for certain things. Okay, so let's go back to the previous classes. We talked about how Drude's law is very, very genius, and it's talking about how you can give electricity and heat a single language, and the electric and the thermal properties of a material can be explained in a single framework or a single theory. So that was kind of the merit of Drude's law. But as we will see that, as we also saw earlier, that there was problems with the Drude's law, and when investigated further, it was found out that the Drude's law was massively bad, and it was overestimating certain things, it was underestimating certain things, and this overestimation and underestimation somehow cancelled in cases of certain physical objects or certain physical observable quantities. So, for example, if you remember, we talked about the Lorentz numbers. So, in those numbers, it was very, very clear. It was very, very similar to the experiments, but it was later found out that it's actually the cancellation of two opposing errors, which was like massive errors, 100-time error. So that is something we are going to discuss today. And also um, we are going to see that what was the timeline of Drude's model being rolled out, and how were the scientific community, and what were the experiments that were not explained that the Drude's model could explain, so it gained traction or it's gained popularity, and what was known to be broken, and how that break or how that mistake was later interpreted and corrected by Sommerfeld. So that is the whole point, or the whole path we are going to take in this episode. So let us start about a little bit of recap. So let's start about what we studied last time. So we studied Drude's model, and what did we study? We studied that there is electricity. We studied that sigma equals to ne square tau by m, where n equals to density of electrons, e square is e equals to charge of electrons, m equals to mass of electrons. Let's say it's me equals to mass of electrons, and mass of electrons, and also the tau is the characteristic relaxation time. Correct? So that is what we kind of saw. And for the thermal conductivity, we also saw that the JQ, or the current of heat, is proportional to something lambda and grad T, the gradient of temperature, right? So that is what we saw, and we also derived a formula for lambda, which was proportional to V square, and which was combining all of that, we got that the kappa, or the lambda versus sigma, it was proportional to T, which was equal to LT. L was called the Lorentz constant, and the Lorentz constant had a value of like 2.2 into 10 to the power. I forgot the value, but it was like, leaving the value aside, it was very, very near to experiment. L matched experiment. So that is what mattered to the scientific community back then, matched experiments. Okay, so that is what we saw in the last classes. and we saw what was the merit. Again, to reiterate, it was single framework of electricity and thermal conduction, right? Okay, so now there are different things that went wrong with the Drude's model, and we will also see that what are some other classical experiments which Drude's model can actually explain in a very good way. So the Drude's model can explain. So what we will see is we will see something called AC conductivity. You will see something called a plasma frequency. We will see something called Hall effect. These were things which were in which the Drude's model was very successful, and we will also see something called the magnetic effects, the magnetic properties of matter, where the Drude's model was a failure. So where it was a failure, magnetic properties, heat capacity, and but in case of AC conductivity, plasma frequency, and Hall effect, we see that the Drude model is very nice, as in it gives us pretty much nice qualitative or overall picture of what is going on. Okay, so that being said, what we can go on to do is talk about what is AC frequency and why we are looking at these things. So the merit, the mathematical merit of the Drude's law, the mathematical merit is the unified equation of electrons, which was more or less given as m dv tau, or let's say this is the drift velocity, equals to minus ee minus so as we can see that it was uh, p by tau, or m v tau by tau. So that was the kind of the characteristic equation of uh, I think it is not v tau, rather it's v. Yeah, this is v tau. So this is minus ee minus mv tau by, or mvd, let's say drift velocity. So mvd by tau. So that was the characteristic equation of a electron moving in certain conductor. So what we see is that, okay, that's nice, but um, and also in the steady state dv dt will be 0, or dv dt is 0. So that will give us a certain minus ee minus minus mvd by tau. So E here will be not E here will be 1.6 into 10 to the power minus 19 coulomb, and minus E will be actually the charge of the electron, right? So sometimes what we in convention what is done is this is called plus, because E already takes into account the minus sign. So sometimes what will happen is you will see this equation. So yeah, that is something that we you might also see, and that is what is generally written vd equals to mu e, where e already contains the sign and everything, so you don't need to worry about it. Okay, so this equation, so those these are maths things, but this equation, for example, it's very important. It's very important, as in, like, because it is giving us a single mathematical way of expressing things. It's giving us an equation which can be it can be personalized, or it can be changed or modified depending on the situation, right? So and what we are trying to see is we are trying to see that whether there is a steady state that is achieved. So that is what we are trying to see. um, so m dv dt. So now let's say we talk first about Hall effect. What is Hall effect? So Hall effect is something that is very fascinating and very well known, and it was discovered far before Drude published his model in the 1900s. So what we see is, let's say there is a conductor and there is current flowing in and current flowing out, and what is seen that even in the transverse direction there is a potential that develops. So that is something which is developing transverse to the actual potential. So this is the applied potential we app. But while the current is flowing, there will be a transverse potential when a magnetic field is applied. Let's say it's to the perpendicular to um, the let's say it's applied to another transverse direction. So that's this is x, this is y, and this is z. So the current is flowing actually in the x direction. The applied potential is towards x. The magnetic field is towards z, but they in towards y also there will be certain potential difference that will be measured. So that is called Hall effect. So something called Hall resistance or Hall coefficient is given as jx by ey into b, where b is the magnetic field. So given the jx, given the fixed current density, what will be the electric field that will be produced in the y direction? Okay, so that is kind of the Hall coefficient. So this is called Hall coefficient. Drude's model, what it does is, I will not go into the derivation, but what it does is, similarly, just like we saw the equation about the normal conductors, what it does is, it does E plus V cross B. So it can explain the whole thing in the same way, essentially. mv tau by tau, mvd by tau. Yeah. So this is the equation that we are talking about. So, and this is the equation of an electron in a magnetic field. So that is explaining the thing. And if we do the same thing, we make it 0, and then from this equation we calculate this r, then what we get is this. So it's independent. So the key points here, it is independent of the geometry. It only depends on the number density of electrons and the charge. Okay, so is this good? Is this good enough? Yes. So there are two cases here. Experimental. Now we will see that this is what Drude model predicts. But what about the reality? What about the experiment? In experiment, we see monovalent atoms like sodium or potassium, or let's say which are nearly monovalent. They can be very good. They agree. But noble metals, transition metals, zinc, beryllium, zinc, iron, copper, etc., they don't agree. And sometimes what happens is the charge carriers in these metals is not electron, it has a plus charge. It has been experimentally measured and verified that these metals, for these metals, um, the carriers are not electrons because they don't have a negative charge, they have a positive charge. Because what is seen is that in the Hall, when the Hall experiment is done, then the experimentalists, they get reverse ordering or the reverse sign of the potential difference that they should get, assuming if there it was an electron. So that's very fascinating. So then we can see that Drude's model fails here, big failure. So Drude's model will fail here, and so that was about Hall electricity, Hall effect. And we will also see about something called AC conductivity. In AC conductivity, what we do is in the from the outside of the conductor, an electric field of a certain frequency omega will be passed, and or maybe some electromagnetic radiation it could be, and we will see that how the conductivity of the metal changes. So what we found out is the conductivity of the metal will be given as 1 minus omega I omega tau. So what is this? This is a very fascinating, and like it's a more complicated looking expression where sigma naught is just this thing. It's the DC conductivity we saw earlier in the Drude's model, but we can see that there is a imaginary number. So what is that? So if we see, then it can be simplified to show that as we increase omega, the real part of sigma AC will drop, and the imaginary part will have a peak somewhere. So sometimes how it can be interpreted as the real part is uh, the normal conductivity we are interested in. It's resistive. It's resistive. Okay. So it is heat. It is heat being dissipated, energy being dissipated, but this thing is kind of like an inductive thing. So for those who have studied a little bit about inductances, this is inductive. So this is not dissipative. So in this regime, the omega is low, so the electrons move with the electric field. So and so they dissipate energy. Here, the omega is too high, so the electrons in the metal they don't get enough time to actually slosh or move with the electric field which was applied outside. So this is also pretty good, has pretty good experimental backing. Okay, so now we talked about AC conductivity. Now we will talk about plasma frequency. What is plasma frequency? Just like AC conductivity, we will see what happens in the high omega regime. In the high omega regime, what we see is that the dielectric function is given as this. The dielectric function is often given as this. So from Drude's model, this is the calculation of Drude's model. Okay, so this 4 pi ne square by m, this thing is often called the plasma frequency squared. This is how it's defined. So it can be written as 1 minus omega p square by omega square. In omega p square, if omega is equal to omega p, what happens is this dielectric function becomes 0, and it's basically like the electric field does not even do anything to the electric cloud. So that is what. So that is very weird. So what happens is so there is a resonance which is achieved. So the electrons slosh around with the electric field. So I think it is not exactly the right way about thinking that electric field does not interact, but the dielectric function becomes 0. It has a lot of physical and mathematical consequences. So this means that this can be more accurately thought about that electrons are sloshing in resonance with the electric field, and for omega in less than omega p, the uh, material is opaque. So for example, metals. So that's why they are shiny. But for omega greater than omega p, it's transparent. So metals are actually transparent in UV. For metals in UV, in UV, and this is very experimentally very successful. So Drude's model actually predicts the correct plasma frequency in this case. So what we saw is Yeah, so the last thing in the chapter of the failures and success of Drude's model is the magnetic properties. So the most fascinating thing about magnetic properties is that apparently if there were no quantum mechanics, no matter would be magnetic. So magnetism is a completely quantum phenomena. So it was shown as a part of, I think, some paper that the analogy is when we will give a magnetic field. So when if there are currents of this like electrons around the magnetic field because the electrons are moving, right? So but certain electrons will, what they will do is they will try to go like this, then they will bounce off. So they will bounce off, right? So apparently the magnetic field caused by this loop, for example the blue tick loops and the red tick loops, they are mathematically shown to cancel each other. So that raises a serious question. Electrons are not, then it proves electrons are not classical objects. So now coming to the failures, that what was the biggest failure? It was most likely, or like the most unanimously, it's the heat capacity problem. So we will talk about a little bit about the heat capacity problem. So what Drude found is that the electronic heat capacity should be this, and the nuclear heat capacity was already known to be this. So the total heat capacity was supposed to be this, but in experiment the total heat capacity was found to be this. So this is theory. This is experiment. So there is a mismatch. This is called Dulong-Petit's law. This experiment thing is called Dulong-Petit's law, and it's very very famous. And also this is only applicable for T very large, very larger than absolute zero. If it is not larger, then the CV is actually proportional to T, and in the extremely low regime it's proportional to T cube. So CV is more like some 80 plus BT cube for low temperatures. And so yeah, so that is pretty much it. And so this was the biggest failure. And also if we think about it, that what is Drude's model? So that was one of the failure, and the second failure is about the mean velocity. Mean free path can be also talked about. So for example, um, the sigma is ne square tau by n, right? Here you can see that E and M are known, but n and tau are the only parameters of the system. Okay, so what we see is that sigma is measured experimentally, n, E, and M. They are pretty much known. Tau is the one which is measured from this formula from experiment. So tau is not measured, tau is calculated, and tau has no theoretical meaning. So tau is certainly just a number which is calculated from the experiment. So from that point of view, if we calculate tau, it comes out to be around 10 to the power minus 14 seconds in most of the metals. So the mean free path is kind of like, and the velocity which is predicted by the thermal velocity or the drift velocity is this. So yeah, so if we actually take all of this into account, I think that's wrong. Yeah. So I think it's 10 to the power plus 3. So yeah, So like taking all of this into account, what we see is that the mean free path is of the order of 10 angstroms. um, so yeah, I think it's a little bit off about the, yeah, this is the thermal velocity and this is the drift velocity. Yeah, drift velocity is 10 to the power minus 3, thermal velocity is around 10 to the power 5. So the this thing is 10 angstrom, which is around the lattice constant of many atoms or many molecules, right? So what we see is that electrons collide with every atom in this way of thinking about it. So let's say there is atoms, chain of atoms, and the mean free path is just the length between two atoms. It's order of that. So the electrons are actually colliding with every atom. But that is not the fundamental assumption of Drude's model. The Drude's model says that the electron seldomly, very, very rarely, it collides with an atom. So that is where there is a mismatch between experiment and theory. In certain materials, in low temperatures, the mean free path can be of the order of millimeters, and that's very large. That's very large compared to 10 angstroms. So that is one drawback, and and also the velocity is something that we will see is not. It's a very very gross underestimate. So that we hypothesize that the actual velocity should be way higher to make the mean free path way higher. Okay, so and also this plasma frequency thing, it it explains us that the plasma frequency, certain metals are opaque and transparent in certain regimes, but it does not explain the color of the metals. Color? No, not explained. Gold, why is it yellow? Not explained. So these things are not explained by Drude's model, but that's fine because it's a preliminary model that gave us a way of unifying all of these things. So now we will see that what was the timeline like, what was the scientific community looking like back then, and how were things. So let's go to the PowerPoint slide and we will see that how, yeah. So we have Drude's model. So the Drude's model was mainly about the DC conductivity, and it got a very good result in DC conductivity. But before DC conductivity, it explains something else which was done previously that we have talked about, which is Hall resistance, which was already discovered in 1879 by Hall, a scientist named Hall, and it was also explained in correctly, more or less correctly. Later, it was seen that for certain materials it's off, but it was pretty much good for certain materials. And so the after the Hall resistance came DC conductivity. Then we have the heat capacity, that is the massive failure of Drude model. So what was thought as so heat capacity was completely wrong. The Drude's model was not being able to see the heat capacity, and it was not being able to predict the heat capacity correctly. Uh, then why was Drude's model still used for other things like magnetism, plasma frequency where it succeeded, magnetism where it failed? So that is because, and plasma frequency means also AC conductivity, because it was seen that for certain things Drude models work, but it was a known problem that Drude model is broken when it comes to heat capacity. No one actually knew that why is Drude model broken, but it was like a pretty much good model for a lot of things. It was a pretty much good model for also for magnetism. It actually could explain certain things, but it was off for certain things. Um, it actually gave rise to the Curie law for certain cases, but that was Curie's law is not applicable every time. So we can see that okay, for plasma frequency, for DC conductivity, for AC conductivity, for large scale, the large scale phenomena where there is no thermal velocity length related. So conductivity does not have any length kind of things. Plasma frequency also does not have any length kind of things. It depends on the total electronic density. So those theories worked, what things did not work, where it had something to do with the temperature, velocity, mean free path, and these things. So cryogenic measurement later on could actually extract out the electronic heat capacity, and it was seen that the Drude model actually predicted the heat capacity to be 100 times larger than what it actually was, and it predicted the velocity of the electrons to be 100 times smaller than what it was, and those things cancelled out to give us the correct Lorentz number in the previous that we have explained in the previous episode. So that is why we come to the new model which are going to discuss in the next class, which is called the Sommerfeld model, which is the quantum model. So he applied. So what was thought? It was thought that Drude model is pretty much okay, but there are some minor corrections needed because it breaks in the case of heat capacity. But what Sommerfeld discovered what was far more serious, that the Drude's model's underlying distribution of velocity itself was wrong, and that's why we were getting such absurd answers, but some answers were cancelling out. So yeah, in the next class, what we are going to do is we are going to talk more about the Sommerfeld model and how it's fundamentally different from today's model. And one thing we are going to see and compare is that um, I think it's very very important also, is that why Sommerfeld model and today's model actually agree on certain things. As in, Sommerfeld model also predicts the correct DC conductivity, the correct plasma frequency, and all. And Drude's model also does that. So we will see that why they work. Drude's model works in certain cases and it doesn't work in certain cases. So that is, I mean, very very fascinating, and that's very very interesting. And we have to also understand the timeline. I will talk more about the timeline in every video because it's very very important to talk about the timeline and to see that how the scientific community was back then. So for example, we you can look up the uh, lives, the personal lives of these scientists, and you will see that they are having complete different dimension of how the scientific community reacted to certain new ideas. And that is very very nice, that is very very something worth looking at. So yeah, see you at the next class then. Till then, good luck and thank you.